Okay, so let's get started. So for this last lecture, I wanted to talk primarily about disk dispersal. And I'm going to begin by discussing photoevaporation. And I'd like to begin by just stating that in terms of what we believe to be the processes that disperse protoplanetary disks, photoevaporation is, far and away the process that most people think is responsible for removing the gas at the end of the disk lifetime. So I'll discuss a little bit about photoevaporation, just try to go through the basics of that. Photoevaporation is a topic, as we'll see, where the simple theory of photoevaporation is very easy to describe. If we wanted to go into really the details of photoevaporation, particularly for the case of X-rays and far ultraviolet radiation, it turns out to be very complicated. So what I've chosen to do is I'll just discuss the simple part of it and just show some results from more complicated calculations. And then I'd like to discuss actually some other things related to MHD disk winds that originally I was hoping to cover earlier in the week, but which we didn't get around to at that time. And those may be relevant to disk dispersal, probably not, but possibly. They may also be relevant to much earlier phases of disk evolution, actually when soon after the disk has formed. So let's begin by discussing photoevaporation. And this is a process that's been discussed for a long time, even in the context of disks. There was work in the early 80s discussing photoevaporation in the context of star-forming disks, and also actually in the context of disks around massive black holes in galactic nuclei. And the basic idea is that we have the disk, and we've already seen that the disk generally has a sort of non-trivial vertical thermal structure. So it's typically cold in the midplane, but then the upper layers, which are directly exposed to the stellar irradiation, are typically hotter. And the idea in photoevaporation is that the surface of the disk is, by some process that we'll describe, heated to some sound speed Cs, which is relatively high. And the idea is that at some radii in the disk, the sound speed is greater than the Keplerian velocity, or roughly equivalently, the local escape velocity from the star. Okay? Now, if you then just asked how much energy that parcel of heated gas would have, because the temperature is so high, the sound speed is so high, the thermal energy means that that parcel of gas would be, in principle, unbound. So it has enough thermal energy to accelerate, adiabatically expand, but nonetheless pick up some positive velocity at infinity. So that gas is then unbound, and the idea then is that it just flows away from the disk in a thermal wind. Okay? So this is the kind of wind that people long ago discussed in the context of the solar wind before Parker and people like that, before they understood the role of magnetic fields in the solar wind. So just very naively then, if we set the sound speed equal to the Keplerian angular velocity at some radius rg and solve for rg, we get that rg is just gm star divided by the sound speed squared. So this will define some sort of critical radius beyond which we would expect this gas to be unbound and to be potentially able to escape the star very freely. So if the sound speed is high, if we manage to heat the gas to a really high temperature, then this radius will be close to the star. If the sound speed is lower, it will obviously be further away. And if we just substitute some numbers, if you say the sound speed is 10 kilometers per second, which is about what would be appropriate if you managed to actually ionize the gas, so you had the equivalent of an H2 region in a very thin skin on the disk surface, then this formula would give you about 10 AU for this critical radius. Now that's a rather naive estimate because it doesn't take into account the role of rotation. The disk is obviously rotating, and so it has kinetic energy to start with, and so the gas on the surface actually can escape more easily than if it was just sitting there in some sort of bound structure like a planet. And that correction factor turns out to be rather significant. When you account for that, you get a number of about 2 AU given this value for the sound speed. So what this means is that if you could heat the disk so that the surface was at this sound speed, then actually a rather large area of the disk would be unstable to escaping. Even if we don't heat it so strongly, and we'll see later, there are other mechanisms beyond extreme ultraviolet radiation that give a lower temperature to the disk surface. But if the disk is 100 AU in size, even a lower temperature will still have a large region of the disk where this material could escape. Okay? So this is the basically one slide really is enough to basically describe the basic physics of photoevaporation. And you can see immediately why this is an appealing process, because we certainly have processes from the central star that can heat the disk surface, and then there'll be a large range where that heating will be strong enough to allow material to escape. Okay, so that's the basic idea, but then the complexity arises from where the source of this radiation that is heating the disk surface is actually coming from. And there are many variations on a theme here. Okay? So the first thing we might think about is that the radiation we're interested in actually comes from the central star. Okay? And rather like when we were talking about the ionization, or in fact almost exactly like when we were talking about the ionization, different sources of relatively high energy radiation from the star will penetrate to different depths in the disk and heat it to different temperatures. And so here we're not interested in the ionization aspects of this radiation, but actually in what the equilibrium temperature that's produced by that radiation would be. So if we have various possibilities, the highest energy possibility would be X-rays, and then going down we would have extreme ultraviolet radiation. So this would have photon energies larger than 13.6 eV, so this will be enough to ionize hydrogen. And then we can have far ultraviolet radiation between about 6 eV and 13.6 eV, which would dissociate hydrogen molecules, but leave the atoms that we produce neutral. So the central star will be producing these kinds of radiation, and one immediate uncertainty is just how strong these different sources of radiation are. And the only one of these that we have really a very good handle on is the X-rays, because the X-rays are relatively directly observed, and we know that young stars are quite strong sources of X-ray radiation. And in different clusters and so forth, people have worked out what the luminosity function of the young stars is in X-rays for various assumptions about what the stellar parameters are. So for the X-rays, we know reasonably well what the source flux is. For these other sources of radiation, it's a little bit hard. EUV radiation is rather difficult to observe from the Earth, because that's also absorbed in interstellar space. And FUV radiation, the main complexity is that if we have magnetospheric accretion, as we heard about earlier in the week, the gas that's crashing down onto the stellar surface will produce a lot of FUV radiation, much more in principle than the stellar photosphere will, but some of that radiation may be absorbed very close to the star and not impinge on the disk at larger radii. So all these sources of radiation will be there, but in the case of the ultraviolet radiation, there's a little bit of uncertainty often about really how much radiation field the disk sees. So that's heating by the central star. Another possibility is that if the star is part of a cluster, then that cluster may contain very massive stars, which are much more prodigious sources of ultraviolet radiation than a sort of low-mass star with a mass comparable to a solar mass that we're mostly interested in from the point of view of planet formation. So if you're in Orion, say, and you're close to the trapezium stars in Orion, those will be producing tremendous FUV and EUV fluxes. And if you're a low-mass star that is relatively close to the core of Orion, those ultraviolet fluxes from this external source of radiation may be very strong on the disk surface. So this can be important if you're in a cluster, and obviously the more massive a cluster you're in, the higher up the mass function you expect to populate with stars, and so the more important these external sources will be generally compared to the internal sources of photo-evaporating radiation. So these are the basic possibilities, and I should mention there's a recent review led by Richard Alexander and Ilaria Pascucci in Protostars and Planet 6, which goes through in quite some detail how these different sources work, and also something about the observational constraints we have on photoevaporation models. Okay, so let's just first mention that for once, this is a physical process that is not purely a hypothesized process. This is something that we can actually observe in some cases reasonably directly. And here's an example. This is from Orion. And here what you have is a fairly low-mass star surrounded by a disk. And what you have to imagine here is that we have radiation from the massive stars in Orion which are impinging on this disk. So what we think is happening here is that this radiation is photoevaporating the gas from the outer regions of the disk that gas is flowing outwards, and then at some distance away from the disk, it's being ionized. So what you have here is a star plus a disk. You can imagine there's some flow here. The FUV radiation is penetrating through the flow to photoevaporate the gas. The gas is flowing away, and then at some particular radius, it's being ionized, which is producing this rather sharp structure that you see in this HST image. So this is an example of external photoevaporation. Similar sort of flow without the external ionization would presumably take place if we had radiation from the central source, which was doing the photoevaporation rather than from an external source. Okay, so let's just show some results from people who've calculated some of these processes. So if we think about FUV radiation in the core of rich clusters, that leads to rather rapid mass loss, particularly if the disks are large. So there's obviously a distinction here. If we illuminate the disk from the central star, the strength of the illuminating radiation field will fall off as we move to greater distances. If, on the other hand, the disk is being illuminated from outside, then that will be, if you like, a flat illumination on the surface of the disk. So external photoevaporation will tend to favor mass loss from large scales. For internal photoevaporation, it's not quite so clear whether it will be small scales or large scales that will tend to dominate the mass loss process. So what's shown here is the mass loss in solar masses per year. So this would be 10 to the minus 7 solar masses up at the top here, as a function of the size of the disk measured in AU. And here the assumptions about the radiation field have some assumption about how strong the FUV radiation field is, and obviously the results will vary depending on what that radiation field is, which in turn would depend on where in Orion, say, this disk is being situated. But the point to note here is simply that if we have a large disk, say 100 AU or larger, then this mass loss rate from external photoevaporation is rather high. So it's maybe 5 times 10 to the minus 8 solar masses, or perhaps a little bit higher than that. So that's a value that's comparable to or larger than the accretion rate that's observed in many of these young systems. So that would be implying that really there's a very significant effect that the disk is being boiled away from the outside in by this external radiation field. Okay. So we wouldn't expect then to see extremely large disks in environments where the external radiation field was very strong. Now, what about internal photoevaporation? Well, here the basic way in which this is calculated is fairly straightforward. So let's imagine we have the surface of the disk here. So here would be the interior of the disk and the surface. And then we have radiation, which is impinging on the disk from above, coming from the central star. Okay? So depending on what type of radiation this might be the so-called direct radiation field. So we might really, from the surface of the disk, be looking down to the central star and, say, seeing the X-rays directly hitting the surface of the disk with line of sight to the central star. Or it might be radiation that's produced from recombination somewhere else in the vicinity. So if we have a star that's an EUV source, an extreme ultraviolet source, that may be ionizing hydrogen above the disk. That ionized material is recombining and producing new photons, which can then shine down on the disk surface and ionize its surface. But one way or another, this radiation is coming in, and it heats the surface of the disk, this red region, down to some level, down into the disk interior. Okay? Now, if this is extreme ultraviolet radiation, ionizing radiation, then this would be an ionization front. This would be ionized gas, and this would be neutral gas underneath. And the property of ionization fronts is that they're really quite sharp structures. So if this is extreme ultraviolet radiation, there really will be a division of the disk into two pieces, an ionized skin and a neutral interior. If instead we're dealing with X-rays or FUV radiation, there'll be a much smoother transition between the region that's being heated by those radiation sources and the region that's not. Now, if we define the base density of this heated region to be ρ and the sound speed to be Cs, then a rough estimate would say that the mass loss rate per unit area would just be the product of those two quantities. Okay? So then we'd have a sigma dot, rate of change of the surface density, that would be of order ρ Cs, and that would be the rate at which material is escaping this disk in this thermal wind there. Okay? So that would be from 1 square centimeter or 1 square meter of the disk surface. We would then need to integrate that over the whole disk surface in order to work out the total mass loss rate which would be coming from the disk. Okay, so those things can be computed, and actually in the extreme ultraviolet case, this is a relatively easy calculation, which was done analytically by Hollenbach and others now in the 90s. Okay? And so what you find there, making some corrections which come from numerical simulations, is that the total mass loss rate in the wind is something like 10 to the minus 10 solar masses per year for fiducial parameters. So that would be a star with the mass of the sun and an ionizing photon flux that's about 10 to the 41 photons per second. And as I mentioned, we don't really know what this ionizing photon flux from low-mass stars would be very well, but the somewhat attractive feature here is that the mass loss rate, which is the thing we care about, only depends on this photon flux to the 1/2 power. So even though there can be actually large uncertainties in that photon flux, they sort of only relatively weakly propagate into the thing we worry about, which is the mass loss rate. Okay, so that can be done easily, relatively easily, for the extreme ultraviolet case because of the fact that an ionization region has a sharp boundary. So in that case, the definition of the skin of the disk that's heated is really quite clean. The disk is heated and ionized down to some level, and then a very short distance under that level, it reverts to being neutral. Now, for FUV and X-ray cases of photoevaporation, it's much harder to do that. It has to be done definitely numerically. But a variety of works suggests that the equivalent expression for those cases is substantially higher, maybe by 1 or 2 orders of magnitude. Okay? So in the most optimistic case, if you like, the case with the highest mass loss rate, you might be getting mass loss rates of 10 to the minus 8 solar masses per year integrated over the disk surface, for example, from X-ray photoevaporation, with a reasonably realistic assumption about the photoevaporation, about the X-ray flux that is being seen by the disk. So those would be large rates. Those rates would be comparable to the mass accretion rates in many stars. And so again, they would suggest that actually sort of viewing the disks as being primarily accretion disks during the stage we observe them is not completely correct, because quite a bit of the evolution is actually instead being driven by the mass loss rate, which is coming from photoevaporation. Now, here's a plot Leonardo showed already yesterday. What I want to focus on here is this graph at the top, which shows for a variety of calculations where the mass loss is coming from locations in the disk. So as I just mentioned, the general estimates are that FUV and X-ray photoevaporation is quite a lot stronger than extreme ultraviolet photoevaporation. So these curves are not all on the same scale. They've just been normalized to the peak mass loss rates that each particular process yields. Okay? So here we are in scale, in AU. Extreme ultraviolet radiation ionizes the disk, and so the sound speed in that ionized layer is this 10 kilometers per second or thereabouts number. So that's the highest temperature that we think we can attain in the disk surface via these processes, and so the EUV photoevaporation rate peaks at relatively small scales, interior here to 10 AU. And then it drops off rather sharply as you go further away from the star, because the UV flux is dropping off with distance away from the star. So this is interesting from the point of view of planet formation, potentially, because here where this EUV flux photoevaporation would be peaking is where you would be expecting to form the giant planets. And actually, long ago, there were suggestions, for example, that the relatively low mass of Saturn compared to the mass of Jupiter might be caused by Saturn forming further out in the disk and being more strongly affected by photoevaporation than Jupiter was at the time when those giant planets were forming. Then we have these other sources of photoevaporation. This is FUV photoevaporation from calculations by Umagorty. Here you have a peak a little bit further out, maybe closer to 10 AU, and then potentially more FUV mass loss occurring at very large scales, out beyond 100 AU. And then in this blue curve, you have a combination model from James Owen and Barbara Ocolano, where they have extreme ultraviolet and X-ray photoevaporation. And here you can see there's sort of a smoother function here. Quite a lot of mass is being lost from a few AU out to maybe 50 AU away from the star. Okay? So in all of these cases, Qualitatively, what you're getting is the same thing, a photoevaporative flow whose velocity is from a few kilometers per second to 10 kilometers per second, reflecting the temperatures to which this surface part of the disk is being heated. And I think we saw yesterday in Leonardo's talk some discussion about, for example, whether you can directly observe these winds, for example, by looking in neon lines. So there's some possibility of directly observing signatures of these winds flowing away from the outer regions of the disk. Okay, so how does that affect the disk evolution? Well, here's an example from some work Richard Alexander did a few years ago. Here we've got distance from the star and surface density of the disk. So this is going to be a little time evolution movie. And this includes viscous evolution and photoevaporation. And for fun, it also includes a massive planet. So we can see some migration taking place as well. So here is how it works. You get some viscous evolution. The disk spreads. The surface density drops. Here the planet forms. We get some migration. And then eventually photoevaporation takes over, and the disk vanishes in a very short period of time. Okay? So this model had EUV photoevaporation only. So the mass loss from the photoevaporation is relatively small, about 10 to the minus 10 solar masses per year. And so the photoevaporation only takes over and dominates the disk evolution at a rather late epoch. Okay? But the characteristic of this kind of model, and models that include more realistically the FUV and the X-ray photoevaporation, is that it leads to a sharp transition between the disk state and the non-disk state. So the photoevaporation becomes important about now, and you can see the disk is then dispersed very rapidly after that period. Okay, so that was all I wanted to say about photoevaporation. So I think let's take our 5-minute pause now, and then we'll talk about some MHD disk winds and wrap up with a few discussions of observations. Okay, so thermal winds, which we've just been talking about, photoevaporation, those have the rather simple property that they only lead to mass loss from the disk, and the mass that is lost has the same specific angular momentum as the place where the wind was launched from. Okay? So if you ask what that does to, if you like, the angular momentum evolution of the disk, the answer is basically it doesn't do anything, right? There's no torque exerted on the disk surface by the material that is moving away in the wind. That would also follow from the fact that the wind is axisymmetric and is purely hydrodynamic in this case. Okay? So the only effect there is a mass loss. Now, the other possibility are magnetic outflows, which I very briefly mentioned at the start of the week, and those have the property that they do produce a torque on the disk surface. So they are both a mass loss process and also a process that affects the angular momentum evolution of the disk due to the torque that is being created there. Now, if we think about star formation simulations, here's an example from Hennebel and Chardy from a few years back. One of the interesting questions that people look at in star formation is actually how efficient angular momentum removal is during the formation of the star and the formation of the disk in the first place. And since stars are forming from magnetized molecular cloud cores, there will clearly be magnetic fields present in the material that forms the star and the disk. And so as the star collapses and forms its disk, there's the possibility that those magnetic fields will take away angular momentum from that system. And to some level, that is a desirable property because, as we know, fully formed stars have a much smaller amount of angular momentum than the angular momentum content of the molecular cloud cores, the rotating molecular cloud cores that actually formed them. However, there's a potential that this can be too efficient during the initial collapse, so-called magnetic braking catastrophe, in which case the disk wouldn't form at all. Okay? The material would just be funneled directly onto the star, and really there wouldn't be an opportunity for forming a long-lived disk. And again, that might not be completely a bad thing. When we looked at some of those plots of disk fractions earlier in the week, it might be consistent to have a small fraction of quite young stars that had already lost their disks, and perhaps that says magnetic braking was quite efficient at an early time, and that was what prevented those disks from forming. But it obviously can't happen in the majority of cases, because the majority of low-mass stars do have disks. So the bottom line here is, from a star formation perspective, we certainly expect disks to have some net magnetic field threading the disk left over from the star formation process, even if we can't say very concretely how strong that field would be. Now, here's a version of a plot I showed also earlier in the week. How do those magnetic fields that are threading the disk surface act to take away angular momentum? So here's the cross-section of the disk, and here is this net magnetic field, which is now threading the disk. And what we've imagined is that because of the inflow towards the star, that field is no longer completely vertical, but instead it has this bent shape due to the inflow through the disk interior. So the key point here is that if we consider the wind region of the flow, so the region above the disk where the magnetic field dominates, any gas in this region will rotate rigidly attached to the magnetic field lines, providing that the magnetic forces that are coming from the magnetic fields dominate over hydrodynamic forces in the wind. So roughly speaking, if we consider gas here that has some density and velocity, therefore have this much ram pressure, if that ram pressure is small compared to the magnetic pressure of this net field, then the flow will be just rotating rigidly around with the magnetic field, as if the magnetic field was sort of a wire extending out from the disk surface. So out to some region that's normally described as the Alfvén surface, the outflowing gas, which is rotating rigidly, gains angular momentum, and as a result of that, the magnetic field has to exert a torque back on the disk surface to conserve the total angular momentum of the system. So if we define that Alfvén surface to be at Ra, the specific angular momentum of the gas that's rigidly rotating would just be V times R. So that would be the Alfvén surface radius squared times the angular velocity of the disk at the point where that particular magnetic field line comes back to meet the disk surface. So the key point here is that if this Alfvén radius is much larger than the radius where the field line meets the disk surface, so if we go a long way out before we reach the Alfvén surface and we start to lose this rigid rotation of the field line, then a relatively small amount of mass flowing out through this wind can remove all of the angular momentum that is needed for accretion. Okay? So this is potentially a different model, a qualitatively different model for disk evolution, because what this says is that if we had our disk and maybe 10% of the mass was flowing out in one of these magnetic winds, that could actually remove all of the angular momentum from the 90% of the gas that is left behind and allow that to accrete onto the star, even if in fact there was no turbulence, no viscosity, none of the processes we were talking about earlier in the week acting within the disk material itself. Okay? So this would be in principle a qualitatively different channel for disk evolution, where turbulence is not involved, and instead the key player is how much magnetic flux the disk has and how much mass is being lost in the form of one of these MHD disk winds. Okay, so is there evidence that those disk winds are actually present at least in simulations or perhaps in observations of disks? Well, as I already mentioned when thinking about the MRI, I think the new development here is the understanding that turbulence within the disk and the production of a disk wind can sometimes be a connected phenomena. Having turbulence that leads to some angular momentum transport within the disk may go hand in hand with having an external wind, which is also affecting the evolution of the disk. And I showed previously some simulations from local shearing boxes, so little local simulations of the disk, which seem to show evidence for producing disk winds as a sort of byproduct of the MRI in protoplanetary disk conditions. Now, here's a much more recent result from Oliver Gressel and collaborators actually from this year, who've now done global calculations. So this is radius in AU, so this would be 1 AU, 2 AU. So here's a reasonable extent of the disk in sort of the terrestrial planet-forming region. Here's height above the disk. And so these are disk models which include a non-ideal MHD physics and also include a net magnetic field. And the point to note here is that you see these arrows which are showing the velocity of the flow. Within the disk, the flow is basically in hydrostatic equilibrium, but away from the disk surface, you are producing here a global disk wind that is carrying away mass and angular momentum from the terrestrial planet-forming region. And this calculation has a net field defined by the ratio of the magnetic field pressure at the midplane to the gas pressure at the midplane that's about 10 to the 5, except this is, should be 1 over this expression. So the gas pressure should be 10 to the 5 times stronger than the magnetic pressure. So this is a very weak magnetic field, relatively speaking, but nonetheless it does seem to be supporting mass loss coming from the disk on these scales. And something you may note here is that this is 1 AU, so this is interior to the region where we would expect photoevaporation to be causing mass to be lost. So one of the possible observational distinctions of these MHD processes compared to photoevaporation is that because photoevaporation is really defined by a particular temperature, the inner disk should be quite tightly bound, and so it would be very difficult to remove material photoevaporatively from the inner part, whereas in an MHD processes, that can be possible. Okay? So the signature perhaps of an MHD disk wind would be seeing a higher velocity component that originates from closer to the star. Okay, so this is now just a brief digression to something that will be covered more fully in the written version of the lectures. If the net field is important in determining whether there are disk winds and whether mass is being lost from the disk surface, then obviously the next important question we might ask is how does that net field itself evolve? Let's say that we started with a disk from star formation that has a little bit of net magnetic flux threading the disk. Will that magnetic flux remain trapped in the disk, or will it tend to escape from the outer edges of the disk and become less important as the disk evolution proceeds? Okay? So this is a case, again, where there's a standard answer, but where, of course, it's not completely clear whether that standard answer encapsulates all of the physics. So the standard answer is that here we have this disk threaded by a net field, and we assume that there is some turbulence within the disk, which provides both an effective viscosity, which is causing the material in the disk to flow towards the star, and also an effective magnetic resistivity, which would allow magnetic field lines to reconnect in this magnetic structure. So the point here is that if we consider a parcel of gas out here, the characteristic length scale for it to accrete onto the star is, of course, just r. And so the viscous time scale would be r squared divided by the viscosity nu. If, on the other hand, we consider this magnetic field line, which is being dragged in by this flow, you can see here that if we could sort of pinch off the magnetic field across the disk, then actually we could reconnect it, and it would effectively drift outwards. It would become straighter if we were able to join this point to this point via magnetic reconnection. And the point here is simply that the scale on which this magnetic reconnection would have to take place is just something like the thickness of the disk, or perhaps a few times the thickness of the disk, which is much shorter than the distance that the disk has to move in order for the gas to be accreted by the star. So if the turbulence is producing a viscosity and a resistivity which are of comparable magnitudes, the reconnection process that is effectively allowing the magnetic field lines to slip through the disk occurs faster than the dragging of the field by the viscous evolution of the disk towards the star. So what that means then is that if we have some colloidal flux psi, the ability of that flux to diffuse radially due to magnetic reconnection is generally more efficient than the rate at which it's dragged inwards. And a theory for this was developed by Steve Lubo and collaborators now a long time ago. It's recently been revisited by some people in the last few years, and it has actually a rather simple one-dimensional description. The magnetic flux, the colloidal flux that's actually threading the disk, its time evolution has an advective piece and a diffusive piece, and the key point, as I was trying to describe, is that this advective piece depends on the viscosity divided by the radius, and the diffusive piece depends on the resistivity divided by the scale height. And because the scale height is generally much smaller than the radius, this diffusive piece tends to be larger than the advective piece, and so magnetic fields do not get pulled in very efficiently towards the star. And that's probably a good thing, because if we look at stars, even though they have, of course, magnetic flux, they have much less magnetic flux than the magnetic flux that perhaps would be contained in a 100 or 1,000 AU disk that was formed immediately after the star formed. Okay, so then let me just summarize the sort of standard thinking on disk winds. The standard thinking is that, yes, we may have both of these wind processes operating, photoevaporation and MHD disk winds being launched from the disk surface. And the standard thinking is that the magnetic winds are strongest during the formation of the protostar and the formation of the disk phase. And indeed, they may occasionally be strong enough to actually prevent the formation of really a fully fledged disk at all. That's the so-called magnetic braking catastrophe, which must be averted in most cases, but in principle could occur in some cases. Now, the general thought is that then if there is any net flux left over from this early phase, that flux presumably escapes from the disk, for the reasons I was describing on that previous slide. The diffusion process that could allow the flux to escape can in principle be more efficient than the dragging in of magnetic field by inflow towards the star. And if there is any net flux left over, that small net flux plays its main role in stimulating the magnetorotational instability later in the disk lifetime. So as we showed earlier in the week, having at least a little bit of magnetic flux left over can be quite important for giving high enough levels of turbulence by MHD processes in the outer disk. And then disk dispersal is a thermally driven process, and the general interpretation of a large amount of numerical results is that if we're not in a rich cluster, it's probably X-ray or FUV photoevaporation that dominates that process. If we are in a rich cluster, it's the FUV flux from massive stars, which tends to boil away the disk from the outermost inward. Now, I would mention just something I've thought about recently. Of course, it's not obvious that if these magnetic winds are important early, it's not obvious that they're not also important at later times. And that would be particularly the case if some parts of the disk are not turbulent, because it's the turbulence within the disk that gives us the potential for magnetic flux to actually escape from the outer regions of the disk. So if there are regions of the disk that are only rather weakly turbulent, then any magnetic flux that's trapped in the disk at early times won't have anywhere to go, and then as the gas accretes onto the star, in fact, that magnetic flux will relatively become more important compared to the gas pressure at late times. Okay, so that was all I wanted to say about winds. So let me now just finish up with a few remarks about observations, and start maybe with a review by Jim Pringle about accretion disks, which many of you may have read. It's a rather sort of famous, simple review of accretion way back in 1981. And at the end of that, he sort of summarized a lot of theory about disks, but finishes with the point that just thinking about theory is not sufficient, and we are likely to learn more about the properties of accretion disks by observation and modeling than by pure theorizing. Okay? So he was talking about disks in cataclysmic variables and X-ray binaries and places like that. I think what we've seen this week is that if we then sort of try to apply the same theory to protoplanetary disks, we have a lot of interesting complexities, but they are actually additional complexities that are over and above those that are already encountered in studying accretion disks in more high-energy environments. The very cold conditions we have in protoplanetary disks, and therefore the importance of non-ideal MHD, the potential importance of thermal processes that might give rise to vortices and so on, those are all properties that are quite difficult to model. So clearly, just from the point of view of theory, we're not going to be able to work out what's going on in disks just by doing better and better computer simulations. We need some constraints from observations. And this is clearly the exciting new thing in the protoplanetary disk field, which we've heard quite a lot about this week, that really just in the last few years, we've gone to a situation where from having relatively few direct observations of disks, we have this wealth of observations of disks that really start to resolve the disk structures on interesting scales and measure a variety of properties of the disk that are relevant to how it might evolve and what its role might be in planet formation. So observational tests of the sorts of models we've been talking about this week sort of come in two classes. The ones we were discussing yesterday were so-called sort of large-scale disk structures that might be produced from some of the disk processes we've talked about, zonal flows, vortices, things that might produce the transition disks that we heard about yesterday, and these may be directly observable in either the density field or in the velocity field that can be observed directly in disks. Now, I wanted to mention just something, just actually to expand on something that Leonardo was saying yesterday. There's a second class of observational tests which would try to measure the small-scale velocity field or the small-scale density field that would have a more direct relationship, perhaps, to whether these disks are turbulent and therefore what role that turbulence might play in early-stage planet formation. So this is really just a different version of things Leonardo said yesterday. If we think about the molecular line width that would be produced in protoplanetary disks, then that has various components. So if here we have a rotating disk and we're observing it at some inclination to the line of sight, the main effect we would expect to see would be the Keplerian rotation. And that will obviously depend on the inclination the disk has to the line of sight. If we happen to look at the disk exactly face on, we wouldn't pick up any line of sight component of that velocity. Then on top of that, we have a thermal component to the line width. And in terms of the way we've defined things, that will depend on the sound speed, which is a factor of h over r smaller than the Keplerian velocity. And then finally, we have a potential turbulent piece to the molecular line width. And in an alpha-type model, the order of magnitude estimate of that velocity is that scales as alpha to the 1/2 times the sound speed. So if we have that estimate of alpha of 10 to the minus 2 that we mentioned right back at the start of the week, we expect the turbulent piece to be about an order of magnitude smaller than the thermal piece, which in turn is a small fraction of the Keplerian piece. Okay? So this turbulent piece is a small effect. It's very small compared to the Keplerian part. It's potentially even small, perhaps by an order of magnitude or more, compared even to the thermal part. But it's potentially measurable if the systematics are well understood. If we really can measure the background rotation field very well, if we can have a good model for the thermal physics in the disk, so we know what this component is, and therefore we can tell if there's an additional component due to turbulence. So I think trying to measure this turbulent component is very exciting because clearly from a theory point of view, that's one of the things we understand least well about protoplanetary disks. Are they really turbulent? If so, what is the nature of that turbulence? And as we've seen, different theoretical models make really quite different predictions for how that turbulence should behave. So here's just an example from some work Jake Simon has been doing with Meredith Hughes recently. What they've been looking at is MHD models, looking at the outer regions of disks, whereas we discussed earlier in the week, ambipolar diffusion would be expected to be the dominant non-ideal piece of the physics describing the evolution. And what's found there, in simulations at least, is that there's a fairly generic prediction for how the turbulent velocity ought to vary with height above the disk midplane. So here we're looking at height above the midplane, and here's the turbulent velocity normalized to the sound speed, here 1%, 10%, and sonic turbulence here. And this gray region here defines sort of an inner part of the disk where ambipolar damping is very strong, and so the turbulence is strongly damped, and you have a sort of ambipolar dead zone in that region with just some active surface layers above and below the midplane of the disk. And what's found here, fairly generically, is that the turbulence levels are rather low in the midplane, and then they climb towards the disk atmosphere, potentially reaching values that are a reasonable fraction of the sound speed if you're many scale heights away from the midplane. So what Jake and Meredith and collaborators have done is to look at the line widths you get from that kind of, or the line shapes you get from those kind of models, and then also the maps you would see in different molecular lines looking at different velocity channels in the data. And what's found here is that from these simulations, you predict that the difference between completely non-turbulent models and the most realistically turbulent models is maybe 10 or 20% in the depths of these double-peaked, of the troughs of these double-peaked line profiles that might be seen from these disks. And then there's some additional constraints from looking really at the morphology of these channel maps. So this is work that's sort of in progress, both from a theoretical point of view and as we heard from an observational point of view. So I think there's actually some prospect of making some progress on really understanding what's going on with the turbulence in disks, now not just from a theoretical point of view, but also by comparing theory actually to direct observations that have the potential to constrain these things. So I expect maybe later in this year we'll have some also results from observations of some of these systems. I should say some of the early attempts at interpreting those observations are coming out with much lower turbulent values, perhaps more like 1% of the sound speed, which, as you can see, would be fairly directly inconsistent, for example, with this particular ambipolar model that's been calculated and shown here. Then let me again finish finally by just picking up on a point Leonardo made about him being focused on looking at boring disks, and other people were focused on looking at exciting disks. And just to emphasize something that I think will also be coming out soon, boring disks are actually very interesting disks from the point of view of constraining disk physics. Okay? So there must be a time prior to which planets have not formed within disks. And at the moment, we don't really know what that time is. So the sort of conventional view, which we've been hearing about this week, is that unless planets form by gravitational instability, the time scale it takes to go from small dust particles up to planets that would be large enough to have a dynamical effect on the disk structure is really quite long. And if we're in the outer part of the disk at 50 or 100 AU, it's really prohibitively long. Okay? So the conventional picture is that there should be a large class of disks in which planets have not formed, and which in that case sense would be boring disks, but where studying those disks should tell us something about the processes that actually lead to planet formation. Now, it's also possible, of course, in principle, that we don't understand something about planet formation, and so it may be that the time when planets are forming is much earlier than conventionally assumed, perhaps even still overlapping with the class 1 phase of YSO evolution. And that indeed is sort of basically what's being suggested for the interpretation of those rings in the Alma image of HL tau. The planets have already formed in that system at a young time, even though there's still an envelope and presumably material still accreting onto that disk. And clearly that's a very exciting interpretation, but it's one also we ought to be fairly cautious about because it's really quite different from what we naively expect theoretically. Now, if we can observe disks prior to planet formation, if that planet formation has not, in fact, all happened at very early times, we were interested in these questions such as how quiescent they are there large-scale structures that might be essential ingredients of planet formation, are they, in fact, populated by vortices throughout the disk, even before any planets have formed, and if they're turbulent, how turbulent are they, and can we can we relate that turbulence, for example, to what's happening in grain growth in the system? And I think as more ALMA results come out relatively soon, we'll probably go beyond just looking at these very, very exciting systems which have dramatic asymmetries and holes and so forth, and try to answer from large samples of disks, really, what do they characteristically look like, and can we see anything directly in the data that really points to what's going on in the early stages of planet formation. So that was all I wanted to say, and thank you very much, and take some questions. Yeah, so the question was about models in which the mass of the planets might be affected by photoevaporation. So the specific models I was thinking about are really very, very old models by Johnson and Hsu and Hollenbach. So those are from the 90s, and so those basically predate any discussions of migration and so forth. So they're not realistic models. On the other hand, I think there is a sort of general point that as we saw, if you have a planet embedded in a gas disk, actually it probably, it's not completely clear, but it probably has quite a ready ability to accrete material from the disk flowing across the gap. And that rate of accretion is quite high for Saturn mass planets. So actually sort of preventing a planet growing beyond Saturn mass is not necessarily a trivial thing. And so it may be that photoevaporating the disk and reducing the reservoir of material does actually play a role in setting some aspects of the planetary mass function. So there could be some interesting physics there, even though the specific models I was referring to are much too simple to make that connection. Yeah, so the question was whether the MRI and disk winch could be operating at the same time. And I think the answer to that is probably yes. I mean, the... Yeah, so the question here is how does the shear in the disk affect the vertical field? So the shear in the disk will not remove the vertical field, right? And so of course because that will be conserved. So at least in principle that could be a long-term stable situation. So you could have a disk that is turbulent on the interior and has a wind produced from the surface, and both processes could persist for a long time. Now, I should say, for example, in those calculations by Gressel and collaborators, when there's non-ideal damping, you may instead have a situation where the disk is not too turbulent in its interior, and a lot of the evolution is being driven by the wind. And so the straightforward interpretation of current work is that at 1 AU, that is in fact what's happening. And I think for the moment it's probably still a bit too new to say that is, if you like, the standard model at the moment. But that's sort of the way that simulations are heading, I would say.
Last question. Okay, so we can